Welcome back to Chemistry, everyone. This is your favorite chemistry series. Today we're going to be talking about, well, we are not talking about fuzzy brown blind animals. We're talking about a number which is very, very important in chemistry. Now, I want you to close your eyes and think of the first thing you can possibly think of when I say the following word. Okay, here's a word. The word is dozen. What's the first thing you think of? Five, four, three, two. Yes, when you said dozen, you said 12. That's the first thing you think of when you think of the word dozen. When you think of the word half dozen, you think of 6. When you think of 2 dozen, you think of 24. You may even know that a gross is a dozen or 144 of something. So the word dozen has a very specific meaning. Okay? So I could have a dozen ducks, right? It's possible. I could have a dozen cupcakes. Yes. I could even go so far as to have a dozen cheeseburgers. Cheeseburgers. So the word dozen doesn't really matter what we're talking about as long as we're talking about 12 of something. All right. Well, I want you to think about, bring this back to chemistry a little bit. And let's talk about, how about a molecule? I'm going to take and draw an H2O molecule. And we all know that one single molecule of H2O is in fact very, very small, and you could never see it with your own eyes. It'd be hard to reach in and pluck out a single H2O molecule. But now I want you to imagine having a dozen H2O molecules. Okay? So we're going to have a dozen H2O molecules. I've drawn two. There's a third, a fourth, a fifth. Wait for it. I'm going to bring them all in. Okay, so I've got a dozen water molecules here right now. And even though it seems like a lot, it's kind of filling up my entire page. This is still too few molecules of water to even see with your eye. Now, we could see this with a very powerful electron microscope, but the problem is, even if you had 12 molecules of water on a like a microscope slide, and you could actually put it into the microscope, you'd still have a horrible time even finding where they are because they're so small. So a dozen water molecules, well, frankly, that's not the type of thing we tend to deal with a lot in chemistry. I'm never going to ask you to go and take 12 molecules of water and put it into a beaker. It's not possible to measure out. So in chemistry, we need a bigger term. We need a term which is able to deal with realistic size quantities of materials. And that term is called the mole. Now, just like the word dozen represents 12 of anything. The word mole has a very specific meaning as well. So 1 mole of anything is going to be equal to this number, 6.02 times 10 to the 23. Okay? That is exactly the same as this number down here. 6.02 times 10 to the 23 is the same as this. This is what's otherwise known as 602 sextillion. It's a huge, fantastically large number. But if I use that number now, the things we tend to deal with on a daily basis, the sizes of materials we deal with on a daily basis, the mole is much more applicable. Just keep in mind, I can have a mole of water molecules. That's like in chemistry speak. Couldn't I have a mole of cheeseburgers? Is it theoretically possible? Yeah, theoretically, it's a lot of cheeseburgers. You'd probably never be able to finish them, but you could have them. You could have a mole of Honda Civics. You could have a mole of coffee cups. I'd love to have even a mole of pennies. I think I'd be the richest person in the world. So in chemistry, when we say the word the mole, we're referring to this number. Now, let me show you what this looks like. Okay, so as we said before, if we actually had 1 mole of water molecules, like what we have here is too small to actually see with your own eyes. I want to show you what a mole of material looks like that you can see with your own eyes. So, something you can see with your own eyes. If you had a mole of copper, this is how much it would be. We've got basically 5 times 4 plus 2. We've got 22 pennies. 22 pennies is about a mole of copper atoms. Just kind of absorb that for a minute. This represents 1 mole of copper atoms. If we assume our pennies are basically made of copper. Just think about that. That means in this many pennies, there are 602 sextillion copper atoms. That's a lot. Let's take a look at it some more. Here's some actual materials you might run across in the lab. Here's those same 22 pennies here. In terms of these are like little tiny BBs or like maybe the stuff you use in BB guns. That's copper. This would be copper's pentahydrate. This is some of the material we're going to work with in the lab. Here's a mole of salt, a mole of sulfur, a mole of sugar, a mole of mercury 2 oxide. Here's a mole of, oh, how'd that get in there? I like this picture a lot because in the little watch glass down here is a mole of salt. Inside the graduated cylinder represents a mole of water, and inside the balloon, a mole of gas. Three different states of matter talking about, but we're actually still talking about how many particles are in each thing. Yeah, I know a balloon has air in it, and this has water, and this has salt. And those are three different substances, technically four, because air is really a mixture of two. But regardless, still represents how a mole of material can be portrayed. It's a lot of stuff. It's something you can physically hold in your hand, right? You hold a mole of copper in your hand, you got 22 cents. You're a rich person. Maybe. All right, well, I digress. So a mole of material represents quite a lot of material. Now the point is this is the type of material we deal with on a daily basis. I don't ask you to deal with a dozen atoms or a dozen molecules. In the lab, we are dealing all the time with moles of material. Okay, so let's do a little bit of analysis. Let's say I have a material you might find at the seashore, calcium carbonate. This is what a lot of shells are made of. So let's say I had 1 mole of this material. And by the way, in chemistry, we tend to abbreviate the word mole as MOL. Like writing that extra letter E wasn't going to cause problems. Anyways, I digress again. So let's say I had a mole of calcium carbonate. Now this is going to be enough stuff. You could probably fit this in the palms of both your hands. It's going to look like a lot of stuff. Well, here's a question for you. If I had a mole of calcium carbonate, how many moles of calcium are going to be in a mole of calcium carbonate? And if you kind of pause and think about that, let's see, I have 1 mole of everything here. So if I have 1 mole of everything, I should have 1 mole of this and 1 mole of this. And so 1 mole of calcium and 1 mole of carbon. How many moles of oxygen do you think are going to be in 1 mole of calcium carbonate? The answer is 3. And if you don't get that, I want you to think about this. Okay, I want you to think about it this way. Instead of thinking about a mole of material, because it is new and the word can be a little scary, I want you to think about a dozen again. Imagine you had a dozen calcium carbonate molecules. If you have a dozen, how many atoms of calcium are going to be in 1 dozen? You are correct. You're going to have 12 calcium atoms. You will have 12 carbon atoms. And because you're going to have 12 times 3 oxygens, you'll actually have 48 oxygen atoms in a dozen calcium carbonate molecules. The other way you could look at it is how many dozen calciums will I have? I'll have 1 dozen and then 1 dozen. So it's going to look very similar. Okay? So moles, dozen, they basically work out the same way. Now, where this entire process gets really interesting is if you go back to our periodic table. And now the numbers that we see here, for example, the number for the mass for carbon, sorry, not carbon, calcium. The mass for calcium is 40.078. Is if you now, instead of assuming 1 atom, if you assume 1 mole of calcium, 1 mole of calcium is going to have a mass of 40.078 grams. So that's the mass of 1 mole of calcium. Oh, how do you like that? So now any number on here, like I could have a mole of chlorine, and a mole of chlorine is going to have a mass of 35.453 grams, or a mole of uranium. A mole of uranium is going to have a mass of 238.029 grams. So now we take something which has seemed kind of odd. Atoms are made of basically the mass comes from protons and neutrons. And now we can say, hey, instead of dealing with a single atom, if I deal with a mole of atoms, now I get something which I can kind of use in my hand. And 40.078, how heavy is that? How heavy is a mole of calcium? Well, I know that 1 pound is about 454 grams, about. All right, so 40.07, this is going to go in here. A mole of calcium is not going to weigh a whole lot. It's going to be a fraction of a pound, but it's still going to be something you can kind of put in your hand and know that it's there. Okay, so if a mole of calcium is 40.078 grams, how heavy do you think a mole of calcium carbonate is going to be? Well, I think your wheels are probably turning. You could probably just add up the masses of each of these things individually. That's exactly what we're going to do. So I will go to look at carbon, and I know that carbon has a mass of 12.01, and I know there's only one carbon in this formula, so that's going to be for a mole of carbon. And now I've got 3 oxygens, and oxygen has a mass of 15.999, pretty close to 16, I know. So if I take 15.999 times 3, that will get me the mass of oxygen in this formula. And what I can do is add up all 3 of these numbers, the result of all 3 of these numbers, and I will get the mass of the entire compound. And if you're still playing along at home, you add those 3 numbers up, you get 100.078, assuming I did that calculation correctly. Actually, I got a different number. I don't know what I was thinking. It's 100.085. All right. So that is going to be how heavy 1 mole, that's in grams, by the way. That's how heavy 1 mole of this stuff is going to be. 1 mole of calcium carbonate is going to be 100.085 grams. And I can do this for any substance on the periodic table. All I need to know is how heavy 1 mole of that material is going to be. Now, this number has a name that we give it because this is the number for calcium. I tend to abbreviate it like this. I say that's the big old MM. That is what we call molar mass. And I can find that for any atom on the periodic table simply by looking at the atomic mass of the number. And instead of assuming the mass of one atom, I assume the mass of 1 mole of atoms. Okay, so this is good for now. Next time we come in, we're going to be talking about hydrated materials and how to convert back and forth between moles to mass and mass to moles. All right, see ya.